I would like to thank the organizers first for this nice event. At FATTOUHI, be sure that we are all happy and nice organization. So my name is Mouad FATTOUHI. Now I'm working as a postdoc in CEA, SpinTech in France. And previously, related to this work, I was doing a PhD in University of Salamanca. So today I'll be talking about some spatiotemporal patterns that appear in spin-orbit torques-driven achiral domain walls. So the first part is related to motivation for this work. And I think the best motivation is to start talking about domain wall dynamics induced by spin-orbit torques. So basically, the conventional way that we are used to is to drive chiral domain walls stabilized via interfacial DMI interactions with spin-orbit torques, since they are the ones that are, the pointer is not working. I'm sorry for this. Thank you. Thank you very much. Sorry for this, and yeah. So I was saying that, okay. So I was saying that conventionally we have driven domain wall stabilized via interfacial DMI interactions with spin-orbit torques, since they are the most efficiently driven with these kind of torques. So despite the complex dynamics of these kind of domain walls, we can map them in simple models, such as the one-dimensional model, where we describe their dynamics as a function of Q, which is the position, and is basically related to the translation of the domain wall along the x-axis. Then another coordinate of this domain wall is the internal angle that describes the orientation of the internal spins of the domain wall along or with respect to x-axis. So in this case, our equations will be written like this. Those are derived from LLG equation. And the dynamics is basically defined by those torques contributing to the equations. So first, there is one torque that is called the damping torque, due to SOT in this case. And this one promotes translation of the domain wall along x-axis. Simultaneously, SOT contributes a precessional torque that tilts the domain wall angle from its equilibrium orientation, which was initially nil, and tries to tilt it like this towards a Bloch configuration. Then, as soon as this torque is able to tilt the domain wall from an L configuration, the DMI torque, or the damping DMI torque, is appearing and trying to restore the initial configuration of the domain wall, which is nil. Then the dynamics is a compromise of these torques, and we can see clearly that the tilting of the angle from the nail configuration weakened this torque and strengthened this one. So due to this competition, the domain wall velocity in general shows a saturation around the critical applied current value. So this value of the saturation is related to the Dzierżynski-Morin interaction field. Well, the question that comes here is that what if we change the way that we use to stabilize nail domain walls from chiral to achiral interactions? Example, in plane anisotropies. So then what if strain is substituting DMI in this case? So what happens is that we have, again, a stable nail domain wall, but this time this guy doesn't have any preferable orientation. Plus and minus x, they have the same energy. And in this case, the dynamics stays the same. However, our restoring torques are anisotropy torques now that are a compromise between the shape and the magnetoelastic anisotropy. And the internal dynamics of the domain wall is defined by, again, the precessional SOT, but then now is an anisotropy torque that depends on sinus 2 phi. What happens is that these two guys, the precessional SOT is getting weaker when the domain wall angle tilts from an air configuration. However, this guy is getting stronger and stronger until the domain wall angle reaches 45 degrees, and then it starts decreasing. So what happens as we increase the current, those torques are like the domain wall angle is tilting from a nail towards Bloch, which cancels all the torques contributing to the dynamics, and then we have a velocity that linearly increases with the applied current until a threshold, and then decreases, and the domain wall stops totally moving. So the reason why this domain wall stops is quite simple. The domain wall angle tilts from nail to block, all the torques are vanishing, and then no dynamics. Then the question that comes here is that, is this behavior universal? So would we have uniform rotation of the internal spins of the domain wall in all the cases? To check whether this is true or not, we decided to run simulations for systems with variable width. Then we have longer domain walls along y-axis. And then when doing so, we found that for the narrowest stripe, simulated stripe, we have something similar to the one-dimensional behavior, where all the spins tilt from a nail to block configuration. However, as soon as we start increasing the width towards higher values, we observe that the velocity increases linearly, reaches somehow around the maximum, and then drops, and the domain wall stops. Clear first deviation from the one-dimensional behavior, which becomes evident if we check what happens inside the domain wall itself. And we found out that there is a nucleation of some special pattern that spreads along the domain wall and keeps the fact that the dynamics is null. So there is no motion. Then we realized that all our models are based on one-dimensional arguments are failing here, and further development of the model is required. What we did is then we extended our model by assuming Walker ansatz for the domain wall for the magnetization spherical angles theta and phi. And this Walker ansatz now accounts for spatial variations of Q, the domain wall position, and psi, the domain wall angle. After some algebra using energy equation, we end up with two partial differential equations that contains effectively the torques that we discussed before. However, new emerging torques here that we call diffusive-like that comes from exchange interaction appear. Why we call them diffusive-like? Because they are related to this constant that is in meters squares per second. So it's just a convention. Then, of course, those torques that were presented before are the same. They depend on the domain wall angle. And one of them is the spin orbit torque, and the other is the anisotropy torque. Then, after realizing that there is some relation with the width of the system, or there is a minimum length scale that you need to put in the system to have these patterns, we decided to check whether these equations can give us a good prediction where exactly those patterns can take place. So what we did is a linear stability analysis, some mathematics. And then this linear stability analysis revealed that there was a critical width above which there will be always this pattern turning. And it's required to have a system with a width equal or above this width to turn those kind of patterns that we have seen before. Here we plot this critical width versus strain. And we can see that the larger is the applied strain, the smaller is the width required to find those structures. So in general, what happens around this critical width is called mathematically a stationary bifurcation. What happens is that the previously stable uniform solution becomes unstable, and two new space-dependent solutions appear, which are energetically equivalent. Only initial conditions will define which one will exist in the equilibrium state. Then after checking the critical width, we decided to solve our partial differential equations in the steady state analytically to find the spatial form that psi and q are supposed to take. And in doing so, we found that psi has a 180 kink form, 180-degree kink form, like the spins are swirling in a 180-degree angle, with a kink width lambda, which is dependent on the ratio of the exchange and the in-plane anisotropy, like any exchange length we are discussing in micromagnetics. Then we compared our analytical prediction to micromagnetic simulations, and they were in good agreement. And this width was found to be around 8.5 nanometers, which is 3 times smaller than the width of conventional vertical Bloch lines that they appear in domain walls in Bloch domain wall dynamics. Then, solving for Q, we got a quite complicated equation. This part of the function is defining the shape of Q, But this guy here is the one responsible on the amount of stretching that the domain wall position will experience. And we can see clearly that this guy is depending on the ratio of the applied current over the exchange, returning back to the fact that there is this competition between the exchange and the spin orbit torque. Again, we had good agreement between micromagnetic simulations and our analytical solution. Then after having a general idea about what happens in the steady state, we decided to check the transient regime and try to understand why those kinks are nucleating in the system. So to do so, we solve our partial differential equations using time domain finite difference with boundary conditions derived from the micromagnetic boundary conditions in absence of DMI, and we compare our results to MUMAX simulations, which are based on a full 3D solution of Landau-Lifshitz-Gilbert equation. And nicely, we can see the animations. Good agreement is found between the numerical solution of our model and a micromagnetic simulation, where the model was capturing all the essential events, including nucleation, annihilation of those kinks, and their interaction with the boundaries. Indeed, it's happening, but the animations are super long, so they will happen around 15 nanoseconds. And if we wait, I mean, it will be too long. Then if you want to see it after the presentation, I can show it to you if you are interested. So then we need to understand why those kinks are nucleated. The best way is to go to those equations and try to track how these torques are changing during this transient regime. And when we do so, we start from an initial state. All the spins are in the, along X in the Nair configuration. Then we apply some current. What happens is that this precessional SOT tries to tilt, as explained before, the domain wall spins from the Nair configuration towards Bloch. However, along the domain walls and near the boundaries, the demagnetizing field is non-uniform. So what happens is that those spins start tilting with different angular velocities. What does this contribute to the system? It increases the exchange diffusive-like torque, this one here. And this guy reverses the spin with the largest tilting, leading to the nucleation of the first kink pairs. Then this nucleation spreads due to the diffusive-like torques along the domain wall, and we reach a state where almost the torques are compensated. So you might say diffusion promoting spatial patterns is not matching the physics we know. But basically, if we were considering these guys here, their role is just to smooth any spatial irregularities. But in our case, what induces nucleation is the off-diagonal terms of the diffusive-like matrix, which are originating from the precession nature of magnetization dynamics. So here, we recap like this transient regime for 3 different widths of the system. And we can see that model is agreeing very well with micromagnetic simulations, where it predicts nucleation of a given number of kinks, then they evolve by annihilation with each other's, or with the edge of the system. And then finally, we reach a steady state where the dynamics is null. So the question that comes into play here is that why we don't have dynamics. So why in this case the dynamics is cancelled? So what happens is that if we return back to the equations, we will see that all the torques that were introduced in the beginning of this presentation are basically compensated or balanced with these diffusive-like torques, which leads to these parts of the time evolution of our domain wall coordinates to cancel out, and then we have no dynamics. If we want some evidence about this, we can see what happens to the torques after 15 nanoseconds of simulation or of the numerical solution of the model, and we can see that these torques are perfectly balancing. So the take-home message from this slide is that the dynamics stop here due to the balance between the diffusive-like and the nonlinear torques. And why I'm saying this here, because we will need it in the last slide of this presentation to understand some extra complicated things that will take place. So another aspect that we wanted to check is how the number of kinks, how the number of the stabilized kinks scales with the size of the system or with the applied current. So we did some systematic, and we saw that by increasing the width of the system, we can see that for a fixed current value, for example, we can choose 200, then we have, if we increase the width, we have higher and higher numbers of kings. So this can be intuitively understood because our equations has well-defined length scales, which were exactly around tens of nanometers. Then if we have larger systems, of course, we are giving room to more spatial modulations to take place. However, the more complicated part is that when we increase the current, we have also increases or changes or like rising in the number of kings. So to check or to understand the mechanism behind this, we choose to track what happens to the domain wall length under the current. And the domain wall length in this case is just measured by taking the local curvature of the domain wall in consideration. So it will be some complex formula. Then I don't bother you with this. And then when we track this domain wall length under current, we can see that if we take, if we sweep the current, and we start from a situation where k is equal 1, k is the number of kings. And then we keep increasing the current, we see drastic increase in the domain wall length. And this drastic increase of the domain wall length explicitly induces drastic increase in the energy. So around the critical current point, the system transits to a non-stationary regime. But then if we keep increasing the current, a second kink comes into play, and then the system stabilizes again, and then its energy is minimized. And this happens for 3 values of the exchange constant that we checked. And for the 3 cases, we have always appearance around some critical current value of some non-stationary states that we will see in the next slide. So a recapitulation about the regimes that were happening or were taking place in these kind of systems. For small currents, what we found always is something that the system have nucleation of some kinks, and then the dynamics is cancelled out, the domain wall is stopped, and then spatial modulations are taking place. So we link this situation to a stationary dissipative soliton that are characterized by always a balance between dispersion, diffusion, and nonlinearity, besides another balance between energy gain and loss. Then if we increase further the current a bit, what happens is that instead of stabilizing or instead of having no dynamics, the domain wall starts oscillating because of the oscillation of its internal magnetization. And this oscillation takes place continuously with a specific frequency, which was here 0.4 gigahertz. So this situation we link it to a pulsating dissipative soliton. And then we have the last situation, which is more complicated. We found that the domain wall, this happens in relatively large current values. We found that the domain wall cracks after a quasi-static phase. It cracks to pieces and recovers. So every time does something like this. And this is a well-known phenomenon in nonlinear optics, for example, and it's called exploding dissipative soliton. So those dynamic states here are for us something new, and that we are exploring for the moment to understand why they take place in such systems. So a summary, we have seen that SOT dynamics of achiral nail domain walls was different with respect to what we know. Then we have seen nucleation of 180 kinks during these dynamics, and we explained why. And then the physical mechanisms governing the kink nucleation during the transient were also unveiled. And then we have seen that these achiral nail domain walls provide an ideal playground to explore complex nonlinear dynamics. And with this, I would like to acknowledge my collaborators, namely my supervisors Luis Lopez-Diaz and Eduardo Martinez, and my collaborators André Tiaville and Felipe Garcia Sanchez, as well as the founding agencies. And I would like to thank you for your attention.